This video is going to introduce Markov chains. What are Markov chains? Well, they're using probability matrices. These are transition matrices, but we're using them in probabilities, and they're quite useful for sort of repeat iterative sort of processes and finding out probabilities by just repeatedly multiplying them until you get to what happens to n tends to infinity or t tends to infinity. Okay, so let's have a look at an example of how we could use these. Based on historic weather, we got some probability information. If a day is fine, then the probability the next day is fine is 2/3. So that's a conditional probability, isn't it? What's the corollary of that? Well, what's the probability that it's wet the next day? Is going to be 1/3, isn't it? Because the two must add up to 1, those two probabilities. Okay, here's my second conditional probability. If a day is wet, then the probability that the next day is wet is 3/4. And from that, we could deduce that the probability that the next day is dry, it would be 1/4. Okay, so let's see the sort of question we might be asked at ordinary A level. Monday is fine. What is the probability that Wednesday is fine? And you'd have just set off and created a probability tree. So should we have a go at that and see where we get to, shall we? Here we go. So here's my diagram. Can I go to that? Okay, so Monday is fine. So first thing I'm going to do is work out what probabilities are for Tuesday. Now, if Monday's fine, my conditional probabilities were 2/3, 1/3 for fine and wet, weren't they? So everything's good. And if Tuesday was fine, what's happening on Wednesday? Well, I can use the same conditional properties 2/3, 1/3, can't I? But if Wednesday was wet, I have to use those conditional probabilities, which are 1/4, 3/4. So now I've created my probability tree. And what was the question they asked me? They wanted to know what's the probability that Wednesday is fine given Monday is fine. Well, I just need to follow those branches that end in a fine, don't I? So it's Tuesday's fine. It's a fine setup to give me this outcome. So that's 2/3 times 2/3, or I could have a wet fine setup event. So it's a 1/3, 1/4. So, and if I do those calculations, 2/3 times 2/3 plus 1/3 times 1/4 gives me an overall probability of that. That probability that Wednesday is fine is 19/16. And if I wanted to, I could find the other probability. What's the probability that Wednesday is wet? By looking at these two outcomes. Here we go. And I would get 2/3 1 times 1/3 plus 1/3 times 3/4, because we'd be following the yellow arms, branches of the tree, which would give me 17/36. Which, of course, if I add these two together, I get 1. That's got to happen, hasn't it? Because those are my two outcomes. Okay, so I could look at writing all of this as a single probability matrix. So let's do that. And if I say that my initial condition, here's my initial condition, probability condition, that's the probability that it's fine on a particular day and the probability it's wet on a particular day. If I want to find the next day, well, what do? I take my probability was going to be fine, multiply it by 2/3, and I take my probability was going to be wet and multiply it by 1/4, and that gives me my probability for the next day that it'll be fine. And I could do the same thing for the wet, and it's the probability that it's 1/3 times the probability it's fine, and it's 3/4 times the probability that it's wet. So you can probably see that everything's looking good here, and I can go from one day to the next using that. Now, some of you, particularly those who are doing computer science, might have seen this as a transition state diagram, in which our two states are fine and wet here, they're in yellow, and we've got little lines or circles or arrows taking us around the things that can happen to go from one to the other. So the probability that it's fine is, what's the probability that it'll be fine again tomorrow? Well, that's 2/3, so I've got an arrow circle going back to fine. And if it's fine today, probability it's going to be wet is 1/3. So I've got those two arrows there. If it starts off at wet, what's the probability it's going to be wet tomorrow's a quarter? If it started off as wet, probability it's going to be fine tomorrow's 3/4. So it's got the same information as we've got here, hasn't it? But what we've done is be clear about today and tomorrow. Okay, so the calculation we carried out earlier to find the probabilities for Wednesday, let's have a quick look. Well, I started off, I knew that it was a fine day, so probability that's fine was 1, probability it's wet was 0. And what did I have to do? Well, I can multiply it by the matrix twice because I'm moving 2 days. If I find the matrix p squared, that's going to be p squared there, 1936, 1736, and 1748 is 3148. And if I start with my 1, 0 initial state, I get the probabilities that I was expecting from earlier. 1936 and 1736 is what I calculated. But you might also have seen that if I'd started off with a 0, 1 setup, I'd have ended up with these probabilities instead. So that would be my other conditional probabilities, wouldn't it? 1748, 3148. There we go. If I'd started out that Monday was a wet day, that's Monday is wet. Monday was wet. Yeah, there we go. Then the probability that Wednesday will be fine is 17/16. The probability that Wednesday will be wet is 31/48. So they're both 48. So that's my summary of my introduction. Markov chains, these are transition matrices, but they're probabilities. And because they're probabilities, the totals here are 1. If I go down a column, 2/3 plus 1/3, or 1/4 plus 3/4 are both 1. I can repeatedly use these to get from day 0 to day n by multiplying by p to the n, just like we did with any transition matrix, and that'll give me my probabilities. So that's part 1. In a minute, we'll have a look at what happens long term in a Markov chain. That'll be my second video.